Okay, so our goal is to achieve sublinear time on all operations, and the approach we're going to take is something called a binary search tree, or BST. So just some kind of thoughts. Linked lists and arrays are linear, so they can be drawn like this or like this. So they kind of keep data in a distinct order, first, second, third, etc. Okay. Back when we were looking at priority queues, we kind of observed that this linear organization wasn't that great for priority queues. So we started off with various types of linear organizations of the data based on priority. But then we reorganized it into a tree. And we found out that that actually had some advantages, particularly for removing the minimum item. So when we were looking at priority queues, we were actually mapping our tree-based structure into an array. But now we'll actually take a look at a linked tree. So instead of storing all of our data in an array, we'll actually use a linked tree. So we'll take the idea of a node from a linked list, and we'll build on it a little bit to have this two-dimensional structure instead of a simple linear one-dimensional structure. Okay, so you might be asking yourself, why are we making it linked instead of using the array? And it's really about the amount of space that may be used. So I'm going to leave that as an open question for a while, but we'll come back to it eventually. Okay, so we're going to be using BSTs, binary search trees. So the name probably means exactly what you'd expect it to mean. So binary, each node will have 0 to 2 children at the most. So binary is in 2. The S stands for search. It'll be good at contains and find. And the T stands for tree. It'll be a tree. So like all of our trees, it'll have a root. And the root is actually kind of where our tree starts at. And consequently, it's where all of our operations will begin. Okay, so just to kind of contrast the binary search tree with heaps, I first want to do a quick review of heaps and the properties of a heap. And then we'll look at the binary search tree, and we'll see that it has some similar but slightly different properties. So our heap had two properties that we enforced. So the first was that it was a complete binary tree, and in case you don't remember, that was really about the shape. It either had the perfect triangle shape or it had the jagged triangle shape where the bottom row was filled from left to right but may not be completely full. So the tree was built kind of from top to bottom, from left to right, top to bottom. The second property that we had was the order property. So that was really about the value of the parent's key with respect to its children's key. So the parent's key had to be less than either of its children, and the children's keys had to be less than either of their children, and so on and so forth. So kind of by the transitive property, this ensured that the root of the tree would have the lowest value overall. Okay, so just as an example, we can draw a quick example of a valid heap. So I'm going to fill in some values here. So imagine we've got 1 at the very top, 3 to its right, 2 to its left, and 5 to its left. Another valid heap would be these 3 nodes, where we've got 1 at the top, 2 at the right, and 5 at its left. Okay, in just a second, we'll look at the binary search tree's properties, and then we will also look at some binary search tree examples and contrast them a little bit with these. Okay, so binary search tree properties are pretty straightforward in terms of shape. It's a binary tree, so we'll kind of ignore that. It's implied by the name, and we'll focus on the other property, the fact that it is an ordered tree. So it has an order property, and the order property is really about the keys in the left subtree of a particular node with respect to that node with respect to the right subtree. Okay, so let's focus on this from the parent node's point of view. So if we've got this node, it's got a left child and a right child. the key of the parent will be bigger than everything that's to its left. All of the keys in that entire left subtree. Okay, so that's kind of the first part of this relationship. It will also be less than all of the keys in the right subtree. Okay, so one of our examples just a moment ago fails this test. The key in the parent is the number 1. So we would expect it to be greater than everything to its left, but it's not. So we'd expect the parent's key, reading backwards, to be greater than everything to its left, and we'd expect it to be less than everything to its right. So it passes the test of being less than everything to its right, but it fails the test of being greater than everything to its left. Of course, we could also think about this the other direction from the subtree's point of view. Everything in this subtree should be less than the parent of that subtree. So 5's key is 5 is not less than 1. So again, it fails our binary search tree test. Okay, so this is a more precise ordering than we have with heaps. Okay, so binary search trees will have nodes, very similar to a linked list. So the nodes of a binary search tree will contain kind of 3 major concepts. There will be the key, and if it happens to represent a map or a dictionary, there will also be the corresponding value for the key. Again, we're focusing on kind of the concepts of sets, so we can think mainly about the access of data. Expanding the concepts we'll be talking about to dictionaries or maps just requires adding this additional value, but we'll gloss over that for now. Okay, so in addition to the actual key that's being stored, we need the links to the 3 surrounding nodes. So there will be a link to the root node of the left subtree, if there is one. There will be a link to the root node of the right subtree, if there is one. And there will be a link to the parent node, if there is one. So let's take a look at a couple of examples and see if they meet our test for binary search trees. So we've got the order property and kind of the overall shape and structure of the tree. So here's our data structures logo. So is this a binary search tree? Well, here we've got letters for the keys, so we have to think about the ordering of the letters in the alphabet. So let's just compare a couple of examples here. So I'm going to compare the root node A to its left child. So again, we'd kind of expect everything in the left subtree, this entire subtree that contains DAT, to come before the key in the parent node. And we can see that there's some counter examples here. The D and the T are letters that are alphabetically after A. Okay, so it passes some tests, but there are certainly examples of where this violates our order property. Okay, let's take a look at another example. Is this a binary search tree? Oh gosh, so we can find some violations of the order property really quickly. The 7, which is to the left of the 2, we'd expect this entire subtree to the left of the 2 to contain values that are less than 2, but clearly it doesn't. Also, there's a node here that has 3 children. It's not even binary. So it's not binary. It's definitely not a binary search tree. Okay, let's take a look at this example. So this example, let's think about 5. Is everything in its left subtree less than 5? Sure. 4. Is everything in its left subtree less than 4? Sure. Okay, and it's definitely a binary tree. This one looks like it passes our test, so it's a binary search tree. Okay, let's take a look at some simple operations. So let's think about the minimum operation. So where is the minimum value in this tree? We can pretty easily spot it visually, but let's think about conceptually where it's at. So 2 is here, right? Let's think about this starting at the root. So the root is 5. If I want to find the minimum value, I want to find something that's less than this. Where do I go to find a lesser value? Well, it'll be in the left subtree, right? And once I'm at this node, I can actually kind of think of this as a recursive process. Basically, I'm kind of at a tree that begins at this particular node. And if I want to find something that's less than it, that would be in its left subtree, right? Okay, so what's the overall pattern? If we want to find the minimum value, we basically just continue to our left as far as we can. Okay, and where's the maximum item? Well, we can exactly reverse what we just described. If we start at the root, if we want to find something that's bigger than the root, we have to move to the right, and then we can kind of think of this as a recursive problem starting at that right subtree. And if we want to find something that is then bigger than the 12, we just continue to move to the right until we get to the 15. Okay, so let's look at this example. Is this a binary search tree? So we could carefully look at each individual value and try and identify if there are any counterexamples. So first of all, 11, is anything in the subtree greater than 11? No, it's not. Everything's less than 11, so we're good there. Could repeat the process with 5, 9, and 3. Let's also look over here, 17. Everything over here is less than 17. That's less than 20, and so on. Okay, if we examine this for a while, we'll find out that it meets our binary search tree criteria. Okay, so where's the minimum in this tree? Again, start at the root node. We want to find something that's less than the root node, less than this new and improved root node, less than this new and improved root node, and so on until we get down to the 2. Okay, so min and max seem pretty easy, pretty straightforward. Let's talk about a more complicated operation. Let's imagine that we want to find the number 15. So I've blocked out part of the tree so we can kind of focus on what happens from the root moving down the tree. So if I'm at 11 here and I want to find 15, what do I know? Well, 15 is greater than 11, right? We can use a similar sort of argument to what we used when we were talking about the concept of binary search when we were searching sorted arrays. So I kind of know that everything to the right, to the left here, would be a dead end. It would all be less than 11. So I can focus on just going to the right. Okay, so if we go to the right, we'll look at the next node. So in this case, it happens to be a 17. And just like we'd argued with min and max, we can think of this as a recursive process that now begins at this subtree. I want to find 15 starting from this node that contains 17. Well, I know everything to the left of the 17 will be less than 17, and everything to the right of the 17 will be greater than 17. 15 is less than 17, so I want to go to the left, and I can throw away everything to the right. Okay, we can continue the process one more time. So we can again start our search from our the node that was to the left of the 17, which is indeed 15, which is what we were searching for. So we're done. Okay, so that allowed us to examine just 3 different nodes and essentially ignore or discard everything else. Okay. So if we wanted to, we could look for the max in this tree. So again, we could basically start at the root. We want something that's bigger than 11, so we'll go right. We want something that's bigger than 17, so we'll go right. We want something that's bigger than 20. There's nothing to the right of 20, so 20 must be our maximum value. Okay, we could search this tree for 16. So again, starting at the root, we know that 16 is greater than 11, so we're going to go to the right and ignore everything to our left. So we'll expand and we'll look at the next node down. So we want 16, but we know that 16 is less than 17, so we'll go to the left and ignore everything to the right of the 17. Okay, that'll take us to the node that contains 15. So we know that 16 is greater than 15, so it won't be to our left, it'll be to our right. Oh, but it turns out that that is a dead end. There's nothing to the right of 15. It's not present. But that raises an interesting question. Where would the number 16 be if it were in this tree? So if 16 were in this tree, it would actually belong at this place where we just stopped. Okay, that's a useful property that we'll come back to momentarily.